Hello, welcome back to another session. And in this session, we are going to discuss memory map peripherals, peripheral memory, and GPIO output, and how to work with CPU registers. All right. So, what is memory map peripherals? Okay. In the CS32V003 and most other modern architectures, we have these control panels. Okay. Just think of a register as a control panel. You change something in the register, you are changing how the peripheral behaves. But the way you change or access these registers is by a memory address or a 32-bit or 64-bit pointer. That is why this is called memory mapped IO. It behaves like memory, but it's not a region memory. Okay. The CPU has single address space for both RAM and peripherals. We call it as a memory map. Now some addresses are read-write, which means that you can both place a value, that is set, or you can get a value. Okay. Now these special addresses directly write into the peripherals. And when you write into one of these special addresses, it doesn't reflect in memory because again, they are memory mapped, but they are not memory. When you can treat them as memory, but when you read or write into them, you are actually changing contents on the peripheral itself. Okay, you are literally flipping a switch or turning a knob on the hardware peripheral. Now zooming in, let me take the example of the GPIO peripheral because that is the topic of this video. And if I zoom in further into the GPIO peripheral or any of the GPIO B, C or C peripherals, we can see that the memory within the peripheral is divided into chunks and each register is made up of 32 bits. Why? Because since it's memory mapped, at any given point of time you can access all 32 bits at a time. Therefore, the register size is also the same as the CPU architecture size, that is 32 bits. All right. So we have the CFG-LR, CFG-HR, which means configuration lower and configuration higher register, the input uh, direction register, out data register, the bit set and reset register. And you see these, we will get into what these registers are. Okay. But you should understand that that's all from the point of view of a programmer, that's all a peripheral really is in memory mapped, the scheme. It's just bunch of memory, and if you change that memory, you're fundamentally changing something about the peripheral. Right? So we'll get into the details, but just understand that every peripheral is just a grouping of certain registers from a programmer's point of view. Now, if you see, each of these registers differs by exactly 32 bits. So the last address is 0, the last address is 4, which means there is a 4-byte gap, there is a 4-byte gap again, and a 4-byte gap again, and then a 4-byte gap again. Right? And I'm showing the least significant bit first. The datasheet might show the reverse. But just understand that these are bit addressable, and each bit, not byte, each bit in a register means something, or it is reserved. Alright? Now let me introduce you the ubiquitous GPIO peripheral, which stands for General Purpose Input and Output. Now, what a GPIO basically is, it is a physical connection of microcontroller to the outside world using the pin. Now, if we consider this as our microcontroller, okay, and this is an LED connected to one of the pin, and this is a switch connected to one of the pin, then physically setting the voltage on this particular pin to high or to 3.3 volt, according to the circuit, would turn the LED on. Similarly, if we enter a switch here, right, so if you press the switch, a corresponding voltage would be generated, and if the peripheral is in the input configuration, it would be able to detect whether the switch is pressed or not. All right, fair enough. So if you zoom in, we see that the GPIO peripheral is quite a complicated beast. It's not so simple like Arduino that you just set something and write the value. Because every other peripheral that has to talk to the outside world, it needs access to the GPIO peripheral, be it UART, SPI, I2C. But we can configure the circuit in such a way that any point of time only one action is performed. That is called peripheral configuration. That we are turning on and turning off certain positions of the circuit so that it collapses into only one function. It is either analog input, alternate function input, reading the registers, writing the value into the pin, or we can configure it for both read and write at the same time, or it can be alternate function output. So we will deep dive into this, but just understand that the IO pin, which is the pin that is exposed outside, is actually having a complex circuit behind it so that it can work as a general purpose input output. Right, so let me zoom back. Now the GPIO pin can take any of the following configurations. So in the blue there are the input configurations, which is the floating input, the pull up input, the pull down, and the analog input, which we also refer to the ADC. And then in the output side we have the open drain outputs and the push pull output. Open drain output is mostly used in bus protocols like I2C, I3C, and SM bus. It's also a variant of I2C. But there are specific reason why an open drain output is required and a push pull is required. A push pull output is stronger and faster and is able to push the value or force the value onto the pin. And an open drain is generally meant to work on a bus. It can set a value, but it won't force it. Okay. And also it is generally safer to use certain times. But for our demo today, we will be using the push pull output. And the third function is alternate function, which means that every other peripheral that wants to use the pin has to be set as one of the alternate function. Alright. Now let us understand the output mode. Now in this video, I'm not going to discuss into the input mode because that's a whole other topic in itself. But we'll do something fairly interesting with the output. Now this is the GPIO peripheral in the output mode. If you see that the input section, that is the top section, is totally cut off, right? So as an output, there are certain registers. One is the output control register, and then the output data register, and then the bit set reject register. Now output control is not really a register because it's just a driver, you can't access it. But for each of the pin, this circuit is replicated. Every GPIO pin is replicated, and the way that you are going to set up that circuit to function is via the registers. All right. So the pathway for the output side is this. Make sense? All right. Now, the GPIO peripheral in output mode can either be push-pull or open drain. Now, if we want to set the value of on a pin, we need to understand these modes. This is this part of the diagram, all right? The output control after the driver, this part. Now, I am representing PMOS this way, Now, if you want to drive the pin logic 1, the PMOS transistor turns on, which means the VDD is supplied. At the same time, the NMOS transistor is also turns off, which means the only way that the current can sync itself is through the pin and whatever peripheral is connected to that pin, right? And if you want to set or force ground, we can cause the current to drain or sink into the pin by setting the logic 0, that is the PMOS transistor is set to off and the NMOS transistor is set to on. So that's why it's called push and pull, because we are literally forcing the value on the pin to be some voltage. It can be either the VCC VDD voltage. VCC is when we are using BJT or the bipolar junction transistors in the older generation. The newer generations are MOSFET based. Now this is open drain output. Now in open drain, you simply use the NMOS part of the output circuit, not the PMOS, not the top part, which means the PMOS control is totally shut off. And we use an external pull-up resistor or an internal pull-up resistor to hold a value. So that will be held at whatever VDD is there at the other side of the resistor, right? And if this NMOS is turned off, the corresponding voltage or the bus voltage can be anything, is given to the pin. And now when we want to read into the bus voltage, we simply turn the NMOS transistor on and the voltage at the bus will be read in. So again, this is not really to set ground or to set a high, but more like listeners and talkers on a bus. So this will be more important when we are discussing I2C. Right. Now here we come to the meat of the topic, which is the register configuration. Now feel free to pause the video and go back and understand the rest or the beginning. Hi guys, hope you're back from the break. So let us get right into the video. We know that in memory mapped peripheral, we just have to access an area in memory to change the configuration of the peripheral. Now, to enable GPIO peripheral, we need to first enable the clock for it. Now, this information on how to set and enable is available in the reference manual, which I will be showing shortly. But for the purpose of this video, just understand that first the clock needs to be enabled for any peripheral to work. So this is the clock enable register, clock control for the peripheral bus 2, and the GPIO C configuration is in the 4th bit. So this is the C syntax to set the 4th bit as 1. Therefore, we have the clock enabled for that particular peripheral. Alright. Next we will see the port configuration register low. Now there is no port configuration register high in this particular microcontroller, but generally the port configuration register is used to set the configuration for the 8 bits of a microcontroller port. Alright, so there are pairs of 4 bits each. Now this is the most important part. These are pairs of 4 bits each, which means for the 0th pin you have 4 bits, that is the mode 0, 0 pin, mode 0, 1, and the configuration of 0, that is in the 2nd position, and the configuration of 0 in the 3rd. So this 4 bits are responsible for the 0th pin. Alright. Similarly, the next 4 bits are in the register are responsible for the first pin or pin 1 in port C, and so on and so forth. So in order to set the configuration of one pin, we need to set 4 bits in this particular register. And what those bits mean? Now, the CNF bits or the configuration bits set the modes that we discussed. Now, this mode, if it is 00 for a given pin, it is in analog input mode, and 01 is floating input mode, and so on and so forth. But the mode which we want for this video is the output mode. Therefore, any pin that we want to set as output, the CNF bits for that particular pin should be 0 and 0. All right. Now, there is another setting called the mode setting, that is these 2 bits. This mode setting basically set whether it's an input or the speed of the output mode. Therefore, along with setting the configuration or CNF bits for each pin, we need to also set the mode as 1, 2 or 3. That is why 4 bits are required for each pin. And to set the data, we have the out DR register. We can also use the bit set reset register. Okay, but for the simple case, writing to the corresponding bit in this register will turn on or turn off the output. All right. So if I want the 0th pin to be turned on, I will set this bit in this register as 1. All right. So take some time to understand this section before we go to the next part, which is the live coding. Now this is the live coding part of the video. Before we start coding, let me tell you what my configuration is. I have connected 8 LEDs to the entirety of port C, that is port C0 to port C7. All of them are connected to the LED, 8 different LEDs in this fashion. Now let me show you the circuit. Now this is the circuit, and as you can see, there are 8 LEDs connected to 8 corresponding pins on the microcontroller, and all of them are right now not configured for output, but that is what we are going to do in this coding session. Right, so let me fire up my Mount River Studio. Right, so let me open a new solution. I'm going to select the microcontroller, and then let us call it blink in sequence. Okay. Now let us go to the main section and just remove what we don't need. I don't need this value right here. I don't need the entire useart section, and I don't need any printf. Okay, this is all I need, and we might not even need the core clock update or the other functions, but just let us keep them for now, and let us try to set up the GPIO peripheral. Now let us go back and check what we need to set. So we need to set the clock first. So this is where we enable the clock for the GPIO-C from the RCC peripheral. We access the APB to PC enable register. Okay, so this will allow us to enable the particular clock for the GPIO-C. Now this is what we call as boilerplate code. Basically this is required. And the next line, here I am totally clearing the entire contents. Now in C, this is a clear operation, bit clear operation, and the entire 32 bits I'm clearing, or I'm telling I just want a complete fresh C peripheral, port C GPIO peripheral. Alright. And here for the each of the bits, I am setting the CNF and the mode. Now the first two are the CNF and the next two are the mode bits of each pin. Guys, observe this very carefully. The first two are the CNF bits and the next two are the mode bits. The CNF bits have to be set to 00 for output push pull, and the mode 3 means it is set at the highest operation. Now this is actually for port C, right? Let me just quickly fix the comments. And this is the fourth pin. Previously I did experiment with port D, but some pins are already mapped. Only the port C was free to account for the entire 8 pins. Now I'm setting up a dummy variable count because I want to set up some sequence of this, and the way to access each pin is using the out data register. So let me just set everything high. Okay, so I have access to the GPIO-C out data register. Let me set everything high. It's 0B 1 1 1 1 1 1 1. Right. Let me build it. And there is a warning that count is unused. It's fine. Let me download it. And fair enough, all bits are high. Now let me change the program to only show the alternating bits. You see, now out data register contains alternating pins. Now I'll go to my build. I will flash and I will check. You see, alternating pins. Now this is the least significant bit. This is the bit 0, and the sequence is starting from here. Now let us try something fancy. Let me see if we can get a waterfall running. I've already written the code for the waterfall. Let me go ahead, uncomment this code, and you can pause the video and go through the logic. Basically, I am using the bit shift operation inside a while loop, and this is already the super loop I have in my program. And then I am incrementing a count variable and going through each pin and setting it to 1, which means the other bits will be set to off. And then once the count reaches 0, I'm going to reset it again. All right. Build the project, flash, and let us see the output. Now, based on what you have learned so far, you can try your own sequences, and having an entire board as output waste 8 pins. So there are much more efficient way to do it. One hint is Charlie plexing. So if you are free, you can go through it, or you can use an I2C port expander. If you know the I2C protocol, to just use 2 pins to control 8 pins or more. All right, so that is all for this video.